Okay, thank you for listening to my pre-recorded talk on the role of gamma ray bursts in our understanding of early galaxies and the reionization epoch. So the reason that gamma ray bursts are potentially useful tools in order to probe reionization is first and foremost because they're so bright, so that means that we can detect them at very high redshifts. You can see here a redshift distribution of the swift detected gamma ray bursts going all the way up now to redshifts 8 and 9. These are obviously ones for which we've obtained the redshift, and of course at the higher redshifts one is only sensitive to the brightest end of the GRB luminosity function, but nonetheless we find bursts at those sorts of redshifts. Secondly, they are created in the core collapse of some massive stars, some class of massive stars, and so we're able to use them to probe star formation and star forming galaxies at all these redshifts. The afterglows, as I'll show you, have very smooth power law continua, and so are ideal backlights for investigating the material along the line of sight in absorption. And of course, now that we know the reionization era is around about redshift 6 to 9 or so, obviously it means that the highest redshift GRBs that we're finding are very much probing that era. And the sort of questions that we want to answer, of course, have been dealt with by a lot of other people in this meeting, but we're interested in the timeline of reionization. That's telling us about the coevolution of the first stars and the first galaxies that they formed in. We want to know about the sources that were chiefly responsible. It's generally assumed it's radiation from massive stars, but of course the budget isn't yet by any means tied down, and so that needs to be established, and we need to find out if there are other sources of reionizing radiation at that time that could have contributed. And of course there's the parallel build-up of chemical elements that are created and dispersed by these early generations of massive stars. So GRBs, as I've said, they're very bright. We can see them at high redshifts. They therefore illuminate a number of key issues, things that we'd like to investigate about this era. So there's a star formation rate at density at high redshifts. I'm not going to be discussing that very much in this talk. I'll say a little bit about the nature of the way GRBs allow us to probe the nature of early galaxies. A very important question is that of the escape fraction of ionizing radiation, and so I'll discuss a little about that. The timeline and topology of the reionization process, dust and chemical evolution I'll mention briefly, and more general IGM probes as well. Okay, so in terms of the stellar populations, the galaxy populations at high redshift, the key point here is that each GRB that explodes pinpoints a host galaxy. It gives us a redshift if we get the redshift from the afterglow, and therefore we can go and hunt for the host galaxies using deep HST imaging, for example, as seen here, with the redshift already in hand. And what we find when we do that is, perhaps not surprisingly, that the majority of hosts are not detected. This, of course, is consistent with the majority of star formation occurring in the high redshift universe happening in very intrinsically faint galaxies that we're unable to detect even at low significance in these deep HST images. In just a couple of cases we have the host galaxy. Of course, when we detect the host galaxy, it allows us to put together the emission properties with the absorption properties and get a really unprecedentedly detailed picture of those galaxies and the interstellar medium that they contain. Results to date, even though based only on a fairly small sample of redshift greater than 6 GRBs and their hosts, are consistent with a steep luminosity function for the galaxies continuing down to something like a cutoff around about -13, but we hope to improve on this in the future. So, as I've indicated, the afterglows and spectroscopy of the afterglows is one of the really key reasons that we're interested in using gamma ray bursts at this to probe these times. And I give an example here. It's a very recent GRB, only went off a couple of months ago. Redshift 6.3, we've got this very beautiful X-shooter spectrum that I'm showing you just a zoom in around the Lyman alpha absorption line. What can we see? We see, well, a number of metal lines as well. And in fact, being an X-shooter spectrum, we have a whole range of metal lines further to the red. Also for intervening gas along the line of sight, in addition to the host galaxy. And then the Lyman alpha line itself, of course, is damped. There's a high column of neutral hydrogen in this galaxy, and by fitting that damping wing, we can determine that column in the host galaxy and also constrain the amount of neutral hydrogen in the intergalactic medium at this around this galaxy. In addition, as it happens, there are two distinct kinematic components in this host, and so that illustrates again the power of the GRB afterglow spectroscopy to probe the detailed physics of what's going on in their host galaxies. Just to be clear what we're seeing when we look at a spectrum like that, of course, in this sort of cartoon I've got here, it shows us looking along the whole line of sight in a sort of logarithmic way back into the heart of a distant star-forming galaxy. And of course, in the middle of that galaxy, we must have some massive star formation that's going to give rise to our GRB progenitor. And then more widely dispersed in the galaxy, we have neutral gas and ionized gas and dust at various distances. And then so outside the galaxy in the circumgalactic medium and along through the intergalactic medium, again, there could be other clouds and other galaxies that we hit. And so what happens when the GRB goes off is, if my cartoon works, that it likely ionizes some of the gas close to the GRB itself within the first few tens of parsecs. But beyond that, we're sensitive to all the gas, and indeed there's evidence that the typical distances that we detect absorption lines from in our afterglow spectra are tens to hundreds of parsecs away. So that's what we learn. Well, there isn't time to go into the details, but if we just look at the metallicity distribution as a function of redshift, then here's a sample where we have robust metallicity determinations, and you can see that it's confirming that GRBs don't occur, it seems, in supersolar metallicity environments, so they require a moderately low metallicity before GRBs will occur. But by mapping the distribution of metallicities, then in GRB hosts, we're able to see the variance, the range of metallicities at given redshifts, right down to very low metallicities that you can see here, and how that evolves with redshift. Looking in more detail at that Lyman alpha line fitting, so what we can see here is the same GRB that we saw before. There's a nice fit to that damping wing, and what we find, in fact, when we look at a whole bunch of GRBs, these are providing us with a whole sample of sight lines into the positions of massive stars in distant galaxies. And we find that the vast majority are like this one. Essentially, there is so much neutral hydrogen there that they're completely opaque to any ionizing radiation. If we look at that whole sample that we've obtained to date, it looks like this. So this is neutral hydrogen column density in the host galaxy as a function of redshift. All the different hosts are there marked as those black points. And what you see is that the distribution is certainly skewed to high column densities. In other words, very high optical depths, essentially zero escaping ionizing radiation from any of those positions of those GRBs. So we're not talking about the GRBs themselves. The important point is the massive stars that they represent. So we're using them as representative positions of massive stars. We see there's little evidence of any evolution, at least between redshifts sort of 2 and 5, which is where the bulk of our statistics are. And so that red line is the median and the pink band is the interquartile range. And so that's sort of indicative of over the range where we have good statistics, there is rather little in the way of evolution. and only a very small number of points, the bottom sort of 3 points or so, where there would be any appreciable escaping ionizing radiation along those sight lines. Now, if we look above redshift 5, there is a suggestion that the average column is decreasing. Perhaps it's doing something like that. The statistics are still not good enough to tell us for sure. If that's the case, then it certainly allows for higher escape fractions, although it's still the case that we haven't yet obtained a non-opaque sightline for any distant high redshift GRBs. But of course, we do need to improve the statistics at that redshift greater than 5 end. However, just looking at the statistics that we have for the whole sample there, what that seems to tell us is that the escape fraction, at least to these locations, is something less than 2%. And so it's certainly problematic for reionization and a puzzle to be solved. Looking forward then to the James Webb era, of course, we'll be using James Webb to look at host galaxies, hopefully, but also to look at afterglows. Even several days after the event, JWST, because of its sensitivity, can obtain very beautiful spectra like this one here. So this is a simulated spectrum of a fairly faint afterglow, and you can see that one can nicely distinguish a combined host and IgM model, which is the red curve that was input into the simulation, from a model in which we only have neutral gas either in the host or in the intergalactic medium, and that's the blue and the green curves there. And so essentially one can decompose those components and constrain the gas in the host as well as the neutral gas in the intergalactic medium. Potentially important, particularly the intergalactic medium part, because it allows us to constrain. We've already seen how the GRBs can tell us about the escape fraction and hence the production of ionizing radiation, the leakage into the intergalactic medium. But if we can measure the neutral fraction as a function of redshift as well, then we can constrain the demand side of the budget, and the potential for that is very good. This is a recent paper by Adam Litz and colleagues, which shows that even for a sample of 20 GRBs above redshift 6, one could construct a timeline something like this, showing the progress of ionization, reionization from potentially up to redshifts 12 or so down to redshift 6 in this particular example. And so even relatively small numbers can constrain that timeline, and especially at the highest redshift end, that's something that's very hard to do in other ways, and so one has potentially a handle there on the behavior at the very early stages of reionization. It's also important to point out that GRB hosts are typically very average galaxies. They're small, as we've already seen, and therefore they're not likely to be highly biased tracers of the matter distribution in the universe. So they're likely to give us a good overall sampling of the intergalactic medium at these early times. Okay, so quickly on to my conclusions. I've shown you that GRBs offer independent windows into the star formation processes and metal enrichment throughout cosmic history. JWST and then later the 30-meter class telescopes through afterglow spectroscopy will allow us to study the interstellar media and the intergalactic medium around these distant galaxies. Currently, the very low escape fraction that we infer from our GRB samples seems to be in considerable tension by compared to what is required for reionization, if one takes that to be of order 10%. And so that seems to either require very rapid evolution in host properties above redshift 5, or potentially some kind of fine-tuning of timescales such that the GRBs that are coming from massive stars with lifetimes of only a few million years, conceivably they are exploding just before the galaxies are on a large scale very largely cleared of gas, and so then one could suddenly have a very high escape fraction for a later period of time. I think it's still a difficult thing to arrange, and so very interesting to see how that story unfolds in the coming years. And then finally, I pointed out that the IgM neutral fraction is proximate to the burst, can be also determined, and so we have something to say about that timeline of reionization as well. So thank you very much for listening.